Precalculus, Chapter 2, Day 5 notes. Lots of stuff right here, good stuff. So let's get after it. Okay, we are going to start with the fundamental theorem of algebra, which is something that you already knew, but now here's a intelligent sounding theorem to go behind it. Okay, and it tells us that every polynomial that has a positive degree with complex coefficients has at least one complex zero. Okay, complex numbers can be written in the form a plus bi. Okay, every real number that you know is a complex number. Every imaginary number is a complex number. Right. It then follows that a polynomial with degree n has exactly n zeros or roots. Okay, we've done this already. All right. So, for example, if you look at h of x is a fourth degree polynomial because the highest exponent that is listed there for the x's is the 4. X to the fourth is the highest degree that they have. Therefore, there are 4 complex zeros. Now, that may be 4 unique or not 4 unique. It may just be, 2 different zeros, but they may both have multiplicities of 2. But if you add the multiplicities together of all your zeros, you got to come up with 4 for this particular function because of the fundamental theorem of algebra. Okay, and that's it for that. Okay, complete review. Descartes' rule of signs. This one's kind of fun. If we want to know how many positive real zeros are in a function, so graphically, how many times does the graph touch the x-axis on the right side of the origin? Those are positive real zeros because it's a real number line, and to the right of the origin would be positive x values. We can find that out with Descartes' rule of signs, which is kind of neat. If you just look at in order, okay, you don't need any placeholders. This isn't synthetic division. You don't have to add 0x if there's no x to the first. Okay, just take the signs, and we are going to just identify them as positive terms or negative terms. So this x to the fourth, the 2x to the fourth, the 2 is positive. Minus 3x to the third, plus 4x squared, minus x plus 5. So all we have to do is identify sign changes. How many times do we have a plus turn into a minus, or a minus turn into plus? Okay, so positives to negatives, negatives to positive. So we look right here, right off the bat, we have a plus that goes to minus. That's one sign change. Then we have the minus going to plus. That's a second sign change. Oh, look, plus goes to minus. That's a third sign change. And then finally, minus goes to plus. So there are 4 sign changes, okay? 4 sign changes. So therefore, by Descartes' rule of signs, there will be 4 positive real zeros, or because non-real numbers, imaginary numbers, if they're going to be zeros, they come in pairs. We're going to be able to subtract 2 for a possibility of 2 less, or 2 real zeros. And again, you got to subtract 2. There may be 0 positive real zeros. Okay, but you know it's not 1, it's not 3, it's not 5, 6, 7. It must be 4 or 2 or 0 positive real zeros. Okay, those are your only options. So if you're looking at your calculator and you see 1 real 0, 2 real 0, 3 real 0, okay, and that's all you see in your window, you know that you got to go further to the right in your window because somewhere over here, that 4th one is there. Because you can't have 3 real zeros that are positive in this particular function. All right, so all they wanted us to find for this first polynomial function was the number of positive real zeros, the possible number of positive real zeros. But what if I want to know how many negative real zeros there might be? Well, they give us a different function, and they said, find the possible negative real zeros. Now, in order to find negative real zeros, you have to figure out what the sign of p of negative x, or in this case, g of negative x, is going to give you. So let's look at the signs that they have right now. If I were looking for the positive real zeros like we just did with the previous polynomial, I'd say, okay, we got a plus, 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 plus. There's no sign changes, so we know there aren't going to be any positive real zeros, okay? But for negative real zeros, if I change x to negative x, okay? Negative x cubed is negative x cubed, okay? If I take negative x and cube it, it's just negative x cubed. Times 3, that would be negative 3x cubed. Notice that the odd exponent, we changed the sign. If I take negative x and square it, I just get x squared. Times 2 is 2x squared. I don't change the sign for the even exponents. So for the odd exponents, 5x, if x becomes negative x, that becomes minus 5x. Plus 7 is always going to be plus 7. Okay, so the signs are only going to change for our odd exponents. So if I'm looking at the sign change of g of negative x, the third degree will change from plus to minus. The first degree will change from plus to minus. These other ones, they don't change, because changing the sign of x will not affect an even exponent. So now we look at minus to plus, that's one sign change. From plus to minus, that's the second sign change. And from minus to plus, that's the third sign change. So 1, 2, 3 sign changes, which means that we got possibly 3 negative real zeros. But if there is a pair of imaginary zeros, then we have to subtract 2 again. Okay? Subtracting by multiples of 2. So 3 or 1. I know that there's at least one negative real zero for that polynomial, and there might be 3 negative real zeros. Okay, so let's look at applying that to these two polynomial functions here. So for p of x, let's look at finding the number of sign changes. Okay, so we have positive, negative, positive, negative, positive. Okay, sign changes. We've got 1, 2, 3. Oh wow, we got 4 of them. That's kind of neat. So 4 sign changes, which tells me there could be 4 positive real zeros. Or you could have a pair of imaginaries, which would bring you down to 2 real zeros that are positive. Or there might not be any positive real zeros. All the positive ones might be imaginary. So how about negative real zeros? So we have the same polynomial here. We're going to change the signs of the odd exponents. So there's to the first. So we've got that minus 3x cubed is going to become a plus 3x cubed. And the minus 10x is going to become a plus 10x. These other signs, they're going to remain the same. We get a plus with the x to the 4th, a plus with the x squared, and a plus with the 15. Well, check this out. There are no sign changes at all. There are 0 sign changes. Therefore, there are 0 possible negative real zeros. Okay? To the left of the origin, that graph is never going to touch the x-axis. Okay? So we're still trying to figure out how to, without a graphing calculator or just without graphing it on a calculator, how to narrow down, how to find where our zeros are. Okay, Descartes' rule of signs is really cool. That's going to help us. The integral zeros theorem just tells me if it's going to be an integer, okay, if one of my zeros is an integer, then it must be a factor of my constant, right? So what is the constant here? Well, it's positive 15. So my factors of 15, which is the constant term, are plus or minus 1. It's always a factor. Positive or negative 3 is a factor of 15. Positive or negative 5. Positive or negative 15. So you got 1 times 15 and 3 times 5. So if your real zeros where the x-axis gets crossed are going to be real, then if you are going to only look for the whole numbers and the negative whole numbers or the integers, then these are your only 8 options: positive or negative 1, 3, 5, and 15. Those are the only possible ones. If you see your graph and you think it looks like it's going through 2 at the x-axis, you know it's not. It might be like 2.1, but it's not 2. How do I know? Because these are the only possible integers that could be x-intercepts of this function. Okay, so that's your integral zeros theorem. Food for thought. This next one, if it's not an integer and you see the graph being intersected at the x-axis by your function, and you say it's definitely not an integer, it's between 3 and 4, but I can't tell if it's 3.5. I can't tell if it's 3.4 or 3.3 or 3. Okay, the rational zeros theorem tells you every possible fraction. Okay, fraction, every possible fraction that is rational. Okay, a rational number by definition can be written as a fraction. Every possible fraction that could be an x-intercept, you're going to be able to list them. Here they are. So we talk about P over Q. Okay, just remember, P is your constant. So P is the constant, and Q is your leading coefficient. Okay. Q, in this case, 6 is my leading coefficient. So 6 is my Q. All right, so in order to figure out all the possible rational zeros of this function, I'm going to take all factors of positive 15 and put it over all factors of 6. All right, all factors, positive and negative, for both of those numbers. So what are the factors of 15? Well, we got plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Okay, we just did it, so we should know that. Factors of 6, plus or minus 1, always. Plus or minus 2 is a factor of 6, plus or minus 3 is a factor of 6, and obviously you have plus or minus 6. Most of the questions that you get are not going to have this many different options, but this one does, so we might as well get it out of the way. So now, all the different combinations here. So let's start when 1 is my numerator. Okay, we got 1 over 1, 1 over 2, 1 over 3, and 1 over 6. Okay, positive and negative. So possible options there: plus or minus 1 over 1, 1 over 2, 1 over 3, 1 over 6. So there's 8 options right there. If plus or minus 3 is the numerator, we got 3 over 1, 3 over 2, 3 over 3, 3 over 6. The only thing that I'm going to ask you to do when you give me your answer, two things. Number one, don't ever repeat your terms. Okay, you'll see what I mean in a second. And then secondly, make it nice. Go from lowest to highest. Okay, so 3 over 1 plus or minus 3. 3 over 2. I haven't listed 3 over 2 yet. 3 over 3. 3 over 3 reduces to 1, and it's already been listed. So I'm going to kindly ask you to not give me 3 over 3 or 1 the second time. 3 over 6. We've already got plus or minus a half, so you don't need to write that one down. Okay, 3's are done. Plus or minus 5. So 5 over 1, 5 over 2, 5 over 3, 5 over 6. So plus or minus 5 over 1, which is plus minus 5. Plus or minus 5 over 2. Plus or minus 5 over 3. And plus or minus 5 over 6. None of those are repeated. Now we'll finish with the 15s. I'll go down here a little bit. Plus or minus 15 over 1. Plus or minus 15 over 2. Plus or minus 15 over 3. 15 over 3 is 5. We've already used 5. So I don't want plus or minus 15 over 3 being written down on this one, because we've already got it. 15 over 6, plus or minus, let's see, 15 over 6, let's reduce it by 3 over 3, 5 halves. We've already got that one. I don't want that written down again, so I am not going to include that last one. Okay. So I'm just going to ask you to go back and put these in order. I'll do that really quickly here. Whoosh, there, I did it. All right, as I said, most of the questions I give you are not going to give you that many to come up with, but these are all of the possible rational zeros that you could possibly get if you are examining the graph of this polynomial. You say, well, why is that important? Well, if it's not one of these, then you're going to have to use the quadratic formula. If it is one of these, you get to factor. Factoring is just a little bit less tedious, maybe a little easier. All right. So if you see, the graph going through the x-axis somewhere between, 3 and 4, you can look right here and say, wait a minute, there are no possible rational zeros between 3 and 4. Therefore, I know that number is probably a square root or something funky like that. Okay, so let's continue. The complex conjugate theorem. So complex numbers, I think I mentioned it earlier, can be written in the form of a plus bi. Okay, a plus bi, any number that you've ever written. If you write the number 5, okay, you could write it as 5 plus no i's. If you have the number negative 100, it could be negative 100 plus 0i. If you have the number 7i, it could be 0 plus 7i. Any complex number can be written in a plus bi form, any of them. So when they say negative 2i, well, negative 2i can also be written as 0 minus 2i or 0 plus negative 2i. So conjugates are fun because when you multiply conjugates, stuff cancels. That's much easier. The conjugates are simply this. If you have a plus bi, you got a minus bi for a conjugate. If you have a minus bi, a plus bi is the conjugate. The only thing that changes is the sign between the real part A and the imaginary part B, BI. Okay, so if I have negative 2i is 1, 0, complex numbers with imaginary parts, they come in pairs. If one of them is a 0, the conjugate's a 0. So if 0 minus 2i is a 0, then 0 plus 2i, which is just positive 2i, is also a 0. Okay? If there's an I in there, they come in pairs. Remember that. One other thing always comes in pairs. Those radicals. No, we're not getting political right now. Radicals, square roots. Okay? If a plus root b is a 0, then just like here before with the complex numbers, all you do is you change the sign in between the two terms. That gives you a conjugate. So a minus root b is the conjugate of a plus root b. And if one of them is a 0, the other one is also a 0 because radical zeros come in pair. Okay, again, not calling anybody radical 0, just saying that's the radical conjugate theorem. So if 3 minus root 5 is a 0, you know by the radical conjugate theorem that 3 plus root 5 is also a 0. Don't even have to do any synthetic division. You know it. If one of them's a 0, the other one's a 0. Okay? That's very convenient. We'll be using that a lot. Okay, location theorem. This one is a lot of common sense. Hopefully you think this is going to be easy. Location theorem, it brings back the reminder that polynomial, when you graph a polynomial, it's going to be smooth and it's going to be continuous. So if I know that there is a point here on my polynomial graph, and I know that there's a point here on my polynomial graph, I know that somewhere between those 2 points, it's got to touch the x-axis at least once, right? Because continuous means I start with my pencil, I can't pick it up while I'm going from left to right on my polynomial. So, I mean, it can be going anything we want over here, but somewhere it's got to touch that other dot, which means there's got to be a 0 between the x value for this dot and this dot. So if you're looking at a table, and again, this should be common sense, but you know, it's something that we can definitely look at to give us an idea of where some zeros are at. If I have a table and I see that there's a negative y value followed by a positive y value or vice versa, I know that somewhere between those 2 x values had to touch the x-axis. It had to have been 0. So I know that between, that's a W, between -8 and -7, there is at least 1 0. How do I know? Because my smooth continuous curve can't go from -7 to 52 without touching 0. Okay, because you can't pick your pencil up and jump over the x-axis. All right, so next up, multiplicities. We've done multiplicities. We know that right here, the bounce indicates that there's a multiplicity of 2. Okay, there's a multiplicity of 2, it's going to bounce. Any even multiplicity is going to bounce off the x-axis. So, you know, that is going to be the -2 with a multiplicity of 2. And then +3 is this factor right here, tells me that 3 is a 0. And because the multiplicity is 2, it bounces off of the x-axis. Okay? Multiplicity of 3. So you've got, you know, an x plus, well, here we have x minus 2 times x minus 2 times x minus 2, or you could write it x minus 2 cubed times x plus 1. So that means that at +2, right, at +2, my 0 is going to be crossed but it's not going to just cross. It's going to flatten as it crosses, just like x cubed flattens as it crosses the origin. X to the first crosses the origin like this, x cubed flattens and has a little inflection point as it crosses. Okay, that should be review. So for each of the following polynomial functions, you need to do all of this stuff. So let's do this. So question 1, I'm going to do all of these for question 1. All right, let's pick a color. Let's pick blue. Determine the number of complex zeros. So by the fundamental theorem of algebra, I know that this is a 4th degree polynomial, so there are 4 complex zeros. They may be real, they may be imaginary, doesn't matter. There's a total of 4 of them, okay? There may be 4 unique ones, or the multiplicities just add up to 4. B, determine the possible number of positive and negative real zeros. So for positive real zeros, let's look at the signs. Okay, the signs as is. We get a plus, minus, minus, plus, plus. Okay, I see 2 sign changes, from minus to plus and from minus to plus. Or from plus to minus, minus to plus. Okay, 2 sign changes. So there are how many positive real zeros? There are either 2 or, subtract multiples of 2, 0. For negative real zeros, let's think about f of negative x. That means that x to the third and x to the first are going to change signs. So x to the fourth does not, x to the third does. X squared does not, x to the first does. And then the 8's always going to be 8. Okay, I see 2 sign changes again. So that means there will be 2 or 0 real zeros to the left of the origin. Okay, for C, the possible rational zeros. So that's the P over Q, factors of P over factors of Q. So we're going factors of 8 over factors of the leading coefficient is 1. So that's nice. Told you it's going to be nicer. Factors of 8. Well, what are the factors of 8? Plus or minus 1, 2, 4, and 8. Now, these are all going to be over plus or minus 1. So that means just going to be the factors of 8 over 1. And I'm not going to write the over 1. So it's going to be plus or minus 1, 2, 4, 8. Okay, if it's not one of these numbers, it's not a rational number. Okay, those zeros, if they're going to be rational, it's got to be one of those 8 numbers. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay, for D, find all zeros using a TI-84, state their multiplicities, and draw a sketch. Okay, so I'm not going to use TI-84, but I am going to use Desmos. So here we are, Desmos. Okay, I have the function typed in. Okay, I've got f of x typed in. Let's graph it. Okay, so if we look at this graph, I see 1, 2, 3 total unique zeros. Okay, so let's look just a second here at the 1 on the negative side. So to the left of the origin, I see 1, 0 with a multiplicity of 2. Now go back to part B, and it said negative real zeros, it's either going to be 2 of them or 0. Okay, we just found 2 of them because there's a multiplicity of 2. Okay, so we've done well there. Remember, positive real zeros, it's either going to be 2 or 0. Well, there's 1, and there's another 1. So our zeros are negative 1, 2, and 4, and negative 1 has a multiplicity of 2. So let's do that. So here we're back to our page. So we know negative 1, multiplicity of 2, 2, and 4. So let's plot our zeros. So -1 is here, and 2 is here, 4 is here. Now you just saw the graphs. You know that it was an up. But if you look at the 4th degree with a positive leading coefficient, you should also know from that you are going to have an up. So we had an up, it bounced at -1, it crossed at 2, and it crossed at 4. Okay, so you should have something like that. Okay, so we have graphed it or sketched it. So now finally it says rewrite in part E, rewrite the polynomial as a product of linear factors. Okay, so we say f of x equals, take our first linear factor. So -1 was a 0, which means x plus 1 is a factor, multiplicity of 2. We have 2 was a 0, so x minus 2 is a factor, and 4 was a 0, so x minus 4 is a factor. We are done with question 1. All right, let's look over here at question number 2. So how many complex zeros do we have? Well, it's a 4th degree again, so there are going to be 4 total complex zeros. Okay, so in this last one, we had 2, 1, and 1 for our multiplicities, so there were 4 complex zeros. Okay, they weren't all unique. One of them had a multiplicity of 2, but there were 4 complex zeros. So positive real zeros. Okay, how many are there? Let's look at Descartes' rule of signs. So we got positive, negative, positive, positive, negative. I see 1, 2, 3 sign changes. So that tells me there are 3 or, subtract 2, 1 possible positive real zeros. Now for negative, we again need to look at f of negative x. Let's change the signs of the 3 exponent and the 1 exponent. Every other sign stays the same. So the 3 exponent was minus, now it's plus. The 1 exponent was plus, now it's minus. Okay, all of those others, keep them the same. Okay, I see 1 sign change from plus to minus once. So negative real number that are zeros, 1. So I know there's one of them, and it's going to touch the x-axis 1 time. Multiplicity of 1, okay? But there's no more than 1. Okay, so what are my candidates for all possible rational zeros? Well, again, we're going to take the factors of p. This time is -128. So we got the factors of 128 over the factors of 1, because it's 1x to the 4th. It's our leading coefficient. So over factors of 1, which means it's going to be just the factors of 128, right? Which isn't too bad. They are right there. 1, 2, 4, 8, 16, 32, 64, and 128. Those are all your factors, and they could be positive or negative. So plus or minus with each of them. Okay, D, find all the zeros using your graphing calculator. All right, so I've taken the liberty of calling on Desmos again. So Desmos gives me, okay, here's your function. Let's graph it. All right, so remember, we had a total of 1 possible negative real zeros. And there it is. And -2 is one of our rational candidates. Over here, I only see 1 positive real zero. So we had said it's going to be 3 or 1. So do I go looking to the right here for 2 more? Well, no, because this is a flattening out. This 0 flattens as it crosses. So this is a multiplicity of 3, right? So -2 with a multiplicity of 1 and 4 with a multiplicity of 3, okay? I've got all of my zeros. Okay, that was pretty quick, right? So let's go back to our note sheet. So there we have it. So we had -2 was a 0, which had a multiplicity of 1. And then we had 4, which had a multiplicity of 3. So let's plot -2. Let's plot 4. Okay. Let's jazz it up a little bit here. Okay, so again, this was an up-up. So we started up. There was a cross at -2. And after the cross, the only thing we had was the flattening as we crossed for the 4. Okay. So we have graphed the second of our our polynomials here, right? Number 2 is done. So if we're going to use the Descartes rule of signs to figure out, am I going to look on the right? Am I going to look on the left of 0? You know, where am I going to focus my attention to find these zeros on the table? Above 0, below 0? Let's look quickly at Descartes rule of signs. And for the positive reals, we have plus, minus, plus, minus. So that's 1, 2, that's 3 possible positive real zeros. Okay, subtract 2. So 3 or 1. Okay, 3 or 1. For negative real zeros, we're going to change the sign of the odd exponents, which is 3 and 1. So this is going to become minus, 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 minus. Woo. So negative real zeros, there aren't any. Okay, so we don't even need to look at negative numbers to see if there might be a 0 there. Okay, that's why Descartes' rule of signs is going to come in handy for us in this one. So let's look at positive and see if we could find 1 or 3. All right, so I have typed this little sweetheart in. Okay, looking at, we don't even have to worry about -2, -1, and below, right? Because we just figured out using Descartes' rule of signs, there aren't any negative zeros that are real numbers, okay? So if we look at 0, there's a -5. At 1, there's an 8. So I know there's a 0 in between there because -5 to 8 has to cross 0. Let me bring your attention down to 3 and 4. 3 for an x has 4 for a y. 4 for an x has -1 for a y. So they went from positive to negative. There's another 0 there. Okay, there's 2 zeros. And then look at 5. 5 is a 0. Okay, you literally look at your table and you get the third 0. So I know that there are zeros between 0 and 1 for one of them, between 3 and 4 for the second one, and I know that 5 is the third one. So let's look at that. So where are they? The location is, there's one between 0 and 1. There's one between 3 and 4. And then there's one at 5. Okay? Now, we just accounted for all 3 possible positive real zeros. So we don't have to expand our table and look to see if there are any more sign changes or zeros. Okay? So those are locations. Okay? Awesome. Okay, number 4, this is probably going to be the easiest of the group. Determine a polynomial, which means it's going to be in standard form, unless it says in factored form. This one doesn't, so standard form. With real coefficients, that has I and -4 for zeros. So if you have I and -4 for zeros, you know one more zero. Remember? If you go back to the complex conjugates theorem, if I know that I is a zero, okay, remember you can write that as 0 plus I, then I know that 0 minus I, which you could just write as negative I must be a zero, okay? Because remember, the imaginary zeros, they come in pairs, and those pairs are conjugates. So in factored form, let's do the conjugates first, because when you multiply them, nice things happen. So for this guy, it'd be x minus I for your first factor. For this guy, it's x plus I. Then for this guy, it's x plus 4. Okay? All right, let's multiply these first two binomials. Okay, let's FOIL it out. So x times x is x squared plus ix minus ix. You could write xi if you wanted to. Minus I times plus I is minus I squared. Okay? And bring down the x plus 4. Okay, let's simplify this thing. Well, this is actually really nice here. This little sweetie pie here and this little sweetie pie here, they cancel. Okay, positive ix minus ix is 0. So that leaves me with x squared minus I squared. Well, remember, I is the square root of -1. So if I square both sides, I get that I squared is, remember the square root and the square are inverse operations, they cancel. I squared is -1. So never give me I squared in your answer. You have to simplify it down to -1. So this is minus -1, which is plus 1. Okay, we're going to multiply that by x plus 4. All right, let's FOIL again. X squared times x is x cubed. X squared times positive 4 is 4x squared. Positive 1 times x, positive x. Positive 1 times 4 is plus 4. Look, there are no like terms whatsoever. So I'll call this f of x. This is a polynomial. It's third degree. Okay. Now you say, why did they say lowest degree? Well, I mean, I could have added another 0 in here. I could have added all the zeros I want, but that would just make the degrees higher. So lowest degree means only do the zeros that they've given you. They gave you -4 and they gave you I. But when they gave you I, the conjugate theorem says -I is also a 0. So if they give you I, they've also given you its conjugate. All right? So that's it for that one. Okay? Whew! It's a lot of good stuff. Okay? I'm looking forward to doing some of those with you in class for activities. Good luck on this practice. If you have questions, reach out. That's it. Okay. See ya.